Okay, welcome to section 2.3, properties of functions. We are skipping 2.2. This is the day 1 video. Okay, so our first objective today is to discuss the average rate of change of a function. Okay, so what is the average rate of change of a function? Okay, so first thing you need to know is that the slope of a line, remember, is m equals y2 minus y1 over x2 minus x1. We're going to start using f of x2 instead of y2. We're going to start using that more often. And instead of y1, we're going to often use the symbol f of x1. Okay? So slope, you used to interpret that as this formula. But what I'm saying is, we would like to update our formula a bit and try and use this version here. M is equal to f of x2 minus f of x1 divided by x2 minus x1. It's the same thing as y2 minus y1 over x2 minus x1. It's just more formal. It's a function notation that we mentioned back in 2.1. Sorry about that. Okay, so what we need to do now is take a look at how this might give us some important information about functions. So let's take a look at an example here. So let's say you're given a problem, and you are asked to find the average rate of change, find the average rate of change of f of x, and let's just assume that f of x is, we'll do something real simple. How about just 5x? From x equals 1 to x equals 6. Okay, so here's what's going on. We have this function. Okay, 5x is actually just a line with slope 5. It passes through origin. Alright, so it looks something like this. Passes through the origin, it passes through this point, because then we rise 5, run 1. Alright, I'm going to go ahead and put our line in there. I'll choose this color. This color. Okay, here we go. Here's our line. Alright. So there's your line. Now if you want to go from x equals 1 to x equals 6, that's going to look something more like this. Right? The point 1 is going to be at 5. Right? When x is 1, y will be basically 5. And then when x is 6, that's way out here, y is going to be 30, because you can just find f of 6, which is going to be 5 times 6, which is 30. Okay, so that's going to be way up here. Alright, so that point is the point 630, and this is the point 1, 5. Okay, so my axis obviously has lots of values between 5 and 30 that I'm not showing. Okay, so when we do that, when we want to express that in math, what we do is, on the y-axis, we draw these two squiggly lines. Okay, so if you look closely right in here, see right there? That section, I drew the two squiggly lines with the gap in between. That means there's a lot of values between 5 and 30 that I'm not listing. Okay, so I got my 5 right here, 30 is like way up there, but I don't feel like drawing the whole thing. So that's a lazy way to abbreviate your axis. Alright, so in any case, your line is going to look something like this. Looks like it's a little less steep now because of the way I did that y-axis, I sort of chopped it there. But the line goes like that, and the question is asking basically, what is the average slope in between here and here, the first point and the last point? So what is the sort of average slope between this point and this point? If that makes sense. Okay, so trying to compare these 2 points. And their slope, the slope of the line that goes between them. So really we're dealing with the slope of the line itself. So this is a really trivial example. Okay, so there's a couple ways you can do it. You can show all your work like this. You can say, okay, f of 6 is 5 times 6 is 30. F of 1 would be 5 times 1, which is 5. And then the average rate of change, which I sometimes call AROC. AROC is going to be f of 6 minus f of 1 all over 6 minus 1, which in our case is going to be 30 minus 5 over 6 minus 1. This is 25 over 5, which is 5. Okay? 5. So what is average rate of change? Average rate of change is the slope of the line that connects 2 points. Okay, so I don't want you to think that average rate of change always turns out to be 5, right? And we don't want to think of it as, okay, look, average rate of change is going to be the slope of the original curve. Some original curves are not straight, right? We don't have to have a linear function. So let's take a look at a different example, a more interesting one. Let's say we applied that same basic idea to this problem. Find the average rate of change of f of x equals 2 over x plus 1 from x equals 1 to x equals 6. Okay, so this is an entirely different scenario. If you'd like to see a graph for this, you can use your graphing calculator, okay? Or you can actually plot it out. It's not a super complicated graph. But something interesting is going on here. So let me just kind of show you what's happening. So you have this more interesting graph. I'm going to skip some of these details on how I'm graphing this, but there is a vertical asymptote right here for this graph. Okay, and there's a horizontal asymptote right here on the x-axis for this graph. Okay, sorry about that. All right, and then we have, for the actual curve itself, I'll draw that again in the pink. We basically have the curve branch like this, and a piece like this. Okay? And then you would like to find the slope of the line that connects x equals 1 to x equals 6. Well, x equals 1 may be like right here. And x equals 6 might be, say, over there. So what we're trying to do is find the location of this point, and then we would like to find the slope of the line between them. Okay? So the slope of the line between them. So something like this. What's the slope of this line? Okay? Alright. So the first thing I need to do is find those 2 green points, or I won't be able to find the slope. Right, so here begins the process. So you write average rate of change is f of x2 minus f of x1 all over x2 minus x1. Okay, the given x's in this problem are your x2 and your x1. So it doesn't really matter which order you pick. I would probably pick the second one to be x2. Okay, so for this problem we're talking about f of 6 minus f of 1 all over 6 minus 1. Okay, so what's this going to give me? Well, I don't know. I'm going to have to plug in 6 into my function. So this is going to be 2 over 6 plus 1 minus 2 over 1 plus 1 all over, and then 6 minus 1. The bottom's going to be easy. Okay, so I end up with 2/7 minus 2/3. No, what am I saying? 2/7 minus 2/2 all over 5. In other words, I have 2/7 minus 1 over 5. And since 1 is really 7/7, what I'm getting is this. 2/7 minus 7/7 all over 5. Negative 5/7 over 5. Okay, so let's simplify that as best we can. This is going to give me negative 1/7. This is my average rate of change for f of x between 1 and 6. So I want you to note something. I want you to note that if I had used something besides 1 and 6, it would have probably given me a different answer, right? Okay, so 1 and 6 was kind of arbitrary. Okay, here's what our textbook likes to do. Our textbook doesn't like to use two numbers like 1 and 6. They like to use 1 and x, or 2 and x, or 0 and x, like that. So let me show you how the book sort of asks questions as well. Okay, so in this problem, a problem like this, they probably would have asked you more like, find, find the average rate of change from 1 to x. Okay, and the function, they give us a function, so we might say for f of x equals, let's just do a new one, how about a square root function? Square root of, and let's just do x minus 2. Actually, I need to get used to the minus 2, I'll use plus 2 there. Okay? So this example, it's just kind of arbitrary, you can pick any function. None of this is all that hard to do, so let's go put this in. Alright, so how would this work? Well, you basically be going like this. The average rate of change from 1 to x would be, okay, remember the rule, you're supposed to do f of x2 minus f of x1 all over x2 minus x1. Well, in this problem, the x1 that they're giving you is right here. This is like your x1. See? And the x2 that they're giving you is like this one. See? So we're going to plug those in. So we're going to be doing square root of, and then we're going to do x2 first. So that is just x, sorry about that, plus 2, minus, and then we're supposed to do f of x1. So that's going to just be 1 plus 2. And all of this is over x2 minus x1, which is x minus 1. So I'm going to take a minute and let you look at this over to see what it is we did. And make sure you understand how I set that up. Okay, so let's see what my final conclusion is. My final conclusion is that the average rate of change between 1 and x is x plus 2 minus rad 3 all over x minus 1. Okay? Okay. Now, what they're going to want you to do with that is they're going to want you to decide now what the average rate of change is from 1 to a number. But they want you to actually use your answer you just got. Okay, so this might have been, let's say, part A of the problem. It would be right here, so part A. And then for part B, they'd say something like, use the average rate of change, use the average rate of change formula from part A to find average rate of change from 1 to 2. Okay, so what I would do in this is, now that I already have my answer for part A, right, which is right here, I'm going to go ahead and just plug in 2. Okay, remember this was A rock, average rate of change, from 1 to X. They want average rate of change from 1 to 2, see? So they're basically trying to tell us that X is 2. This is from 1 to X, from 1 to 2. So let's just let X equal 2. We'll plug that into our previous answer. Okay, so here is our final conclusion. That A rock from 1 to X was this. Right? And so therefore the A rock from 1 to 2 is going to be 2 plus 2 inside that radical minus square root of 3 all over 2 minus 1. So we just end up with square root of 4 minus square root of 3 all over 1. Okay, so the answer is 2 minus rad 3. Okay? Then that would be kind of how your answer is. Okay, now, what we said was, we already kind of talked about what this means. Let me show you exactly what this one means on this problem. Okay, so absolute value, or the square root of x plus 2 is a function that is basically just a radical function shifted to the left 2 spaces. So you should have seen this as early as algebra 1, really. You should know what this graph looks like. Okay, it's a radical function shifted to the left 2 spaces. Okay, so let's go ahead and take a quick look at what the graph would look like. Okay. Alright, so let's draw this. Square root function, usually, just comes right out of the origin. It goes like that. Okay? But this is going to be shifted 2 to the left. Alright? Let's take this sucker and move it over. 1, 2. Okay, another point we know it passes through is negative 1, 1. Negative 1, 1. And what we just accomplished was actually kind of a profound conclusion that we did here. Well, I guess not profound, but just interesting what we were able to accomplish. We found basically the slope of the line that passes between 1 and 2. So I'm going to try and draw that here. Okay, so let's put points 1 and 2 on here. All right. Okay, there we go. So we basically found the equation. Let me try that again. Found the equation of this line right here. I'm not very good with these lines yet. It's basically 1 and 2 here. We found this equation, or we found the slope of this line. That's what I meant to say. Alright, let's get a line going there. That line. The line, slope of that line is 2 minus rad 3. So what is 2 minus rad 3? Well, 2 minus rad 3 is about 0.28-ish. 0.26, somewhere in there. It's just a very small number. That's why the line looks so shallow. Okay? Alright. So do you think we could have, instead of just finding the slope, maybe we might be able to find the actual equation of that line? Okay, so you bet. So that's actually our next goal, is to find the equation of that line. Okay, so part C would be find the equation of the secant line from x equals 1 to x equals 2. So that's that green line. We're trying to find its actual equation. Okay? All right. So how would you find the equation of this line here? Well, the best bet would be to use this formula. Y minus y1 equals m times x minus x1. Let's update this to our new notation. I told you that we were not going to write y1 much longer. Sometimes we will. But we're going to call f of x1. It's the same thing. Instead of slope, m, we're going to write a rock. Okay? And we have it written like this. Okay, so let's go ahead and fill this in. This is actually not very difficult. Remember the points, x1 and f of x1. That's just x1 and y1. It doesn't matter which one you pick. So for x1 and f of x1, that's kind of like x1 and y1. That's what that means. I'm going to go ahead and use the 1 and the f of 1. Okay? Or I guess you could use the 2 and the f of 2. It doesn't really matter. I'll let you decide which you want to use. So do you want to use, let's think about this actually. So if you were going to use this, x equals 1, it would look like that. So it would be 1 and rad 3. That's one option we can use for x and f of x1, x1 and f of x1. Or we could use the other point, which is where x was 2, and then do this. I'm actually kind of liking this one a little bit better. I'm getting 2, 2, see that? That's a little bit cleaner. So I'm going to actually use this one. We already figured out that this was 2 minus rad 3. That's our slope. And then we had just decided that we were going to go ahead and use this answer down here for our point in the point slope form. So we'll put those numbers in, 2 and 2. And this is the answer. If you want to graph it on a calculator or something, you'd have to actually add this 2 to the right. And then you graph it on the screen. Okay? But I'm not really focusing on technology right now, so I'll let you do that if you wish to do that. It's not important to me right now. You would add 2 to both sides. Okay, so this is our first major topic, average rate of change, what it means to find the slope of that line, right? And also we can find the equation of that line. The example I've chosen here is fairly difficult because notice our slope is kind of weird. Slope is 2 minus rad 3. That's kind of weird, but it's just a number, just like any other number. So I'm not afraid to put it there. I did need parentheses on it though, don't I? Okay. Okay, the next thing I'd like to talk about is the idea of increasing functions and decreasing functions, and also maxima and minima. Okay? So let's talk about increasing functions. And decreasing functions. Okay, so what does it mean for a function to be increasing? Okay, so we would say a function is an increasing function if it basically looks like this, on the rise. Okay? And then if we wanted to describe a function as decreasing, it's on the down. So it's going downward. Those are very easy to understand. One slope sort of upwards, one slope sort of downwards. So I want you to think in terms of the way you read, right? You always read left to right in English language, at least. Right, so I want you to think left to right, okay? So if you were walking along this curve from left to right, so that means you're going this way, you notice that the graph is rising, right? So we would call it increasing. Over here, you're still going to think left to right. We always think left to right in math, okay? In graphs like this, we're using words like increasing and decreasing. Okay, so imagine again, you're moving from left to right. This graph is going downhill for a person traveling to the right. Okay, so that's what it means just intuitively. Because obviously we need a more formal definition than that. Okay, so the formal definition is, oops, sorry about that. This bright green line there. Okay, so we have, for a decreasing function, or let's actually do increasing first. How do you recognize an increasing function? If you pick a point on here, you can call it, let's say, x1, comma, f of x1. That's our first point. Okay? And our second point on here, x2, comma, f of x2. The way we would describe this is that although x1 is less than x2, in the same way that x1 is less than x2, f of x1 is less than f of x2. Okay, so this is just another way of saying that x1 came first on the number line, and then x2 came next. So x1 is to the left of x2. And in the y direction, f of x1 is also less than f of x2 because it's below it. Okay? So in the x sense, we have first number and then second number. So x1 is less than x2, see how it's to the left of it? And then in the y direction, we have the same idea. F of x1 is below f of x2, meaning it's less than. Okay, so this is the official definition of increasing. All right, so let me just pull this down. Let's put this here. This is what it means to have an increasing function. Okay, now the entire function can be like that. In some cases, just a portion of the function is like that. Okay, you could probably figure out how to write decreasing function. Decreasing function means the graph is going down as you go to the right. Remember? Let's make our colors consistent. So it's going down as you go to the right. So if you pick any 2 points, let's say this one, this is x1, f of x1. Here's your first point. And your second point, x2, f of x2. Remember, that just means x2, y2. The way you would describe it here is actually x1 is less than x2 still. See how x1 comes first on the number line? So x1 is still less than x2. But if you look at the y values, right, this is f of x1, and it's actually above f of x2. See that? So actually the greater one here is f of x1. It's higher up. So you'd write f of x1 is greater than f of x2. And this is the official definition of decreasing. This is a little hard to get used to, okay, but this is the official definition. Okay? All right, and then the next thing we want to look at is relative extrema. What is relative extrema? Okay, so first of all, just so you know, our textbook doesn't use the word extrema, but next year's book will. Extrema means the extremes. So extrema can mean minimum or maximum. These are just the plural for minimum and maximum, right? So anytime something is the smallest or the largest, of a group. We would call that the minimum and the maximum, respectively, right? Well, in this context, we're talking about points on a graph, okay? And when a point is the highest point, we would call it a maximum, and when it is the lowest point, we call it a minimum, okay? And relative, another word for that is local, okay? Local. So that means nearby. Okay, so your textbook's going to write local max, local min, that sort of thing. Here's what a local max looks like. You can always recognize a local max because the graph will be increasing on this side of the point and decreasing on the other side of the point. Okay? So now it doesn't really matter what else is happening in the graph. For example, this graph might go back up and shoot way up high like that. It doesn't really matter. We're talking about locally. This point in its own little region is technically considered a maximum, right? It's not the highest point on the graph. There are higher points, say over here and here and here. These are higher up. But in this region, locally speaking, he is top dog. He is the high point, okay? So this might be the point C, f of C. Okay, so here's how you would write it. You would say, let's say this is the function, f of x, okay? You would say, f of x has a local maximum at x equals c. Or you can put the value of f of x, I'm just teaching different ways of saying this, the value of f of x at x equals c is f of c, and it is a local max. Okay, and I just want to say it one more time. The word local and the word relative are synonyms. Okay, so I need to say this now because next year, when you're taking calculus, if you are, they won't say local, they'll say relative, right? All right, let's look at the minimum case. All right, so what is minimum? Well, maybe you can fill it in. You can pause the video and try it yourself. It's not hard. It would be sort of the opposite situation, right? Go ahead and just block again. Okay, so here at C, the graph was decreasing. And then there's this point. And then to the right of it, the graph is increasing. Okay, so what's going on at this point? Right here, that point, we have what we call a local minimum. Okay, and it doesn't matter what the rest of the graph does. This graph could shoot down on both sides. Whatever, it doesn't make any difference. There are lots of points down here that are far deeper, further down the page than the one I've circled, but the one I've circled is a local minimum. Why? Here's why. In its region, we have it being the lowest point. Okay? It's the lowest point. So we're going to go ahead and write our explanation for this as well. I'm going to move this down a little bit. Oops. Sorry. So get kind of used to the stylus. It's nice, but it's difficult to use sometimes. Okay, so we would say, we'll just write the first sentence this time. F of x has a local minimum at x equals c. Or you could just write f of x has a local minimum at c. Alright? Alright, so I just want to say one more little thing about that. This is the point c comma f of c. That's how we're going to call it from now on. And I will say this, the value, I will go make this sense actually, of f of x at x equals c is f of c, and it is a local minimum. Why? If you had to justify that, you would say because it's decreasing on the left and increasing on the right.